So let's talk about Rolle's theorem, mean value theorem, and then we'll get on to what's called Cauchy's formula or Cauchy's theorem. So Rolle's theorem states this. This would have been talked about in Calc 1. If, single variable, if f is continuous on the closed interval from a to b, and the endpoints are equal, f of a equals f of b, then you can say that there exists a value c in the open interval from a to b such that f prime of c is equal to 0. And this basically means what? That means slope is 0. So this is implying that slope is 0 at some value of c. So if you take some curve, and I drew it so that the endpoints here at a and b are equal, so this value and this value at b, we can see that those, let me erase that, those are equal. You go up to the line like that, and then you basically are getting this line right here that goes through those 2 points. So it's saying that there has to exist a value c here such that essentially the slope and the tangent line right there is 0. So this is f prime is equal to 0. And you can see that it is, of course. Then the mean, so that's Rolle's theorem. That's the initial one. Then you can use Rolle's theorem here and prove the mean value theorem. So the mean value theorem is a little more powerful. And so what it says is this. I mean, it's more general. It's a general statement. So the mean value theorem, really important, is used to prove a number of things in calculus. If f is continuous on AB, the closed interval from a to b, then there exists a c in the open interval from a to b. F is continuous and differentiable. So f is continuous on the closed and it's always differentiable. Let me change colors on that. Differentiable on the open. So continuous on the closed interval, and then we always say, or it includes f is differentiable on the open interval from a to b. So that's same statement's true for the mean value theorem. Okay, because you have to have that derivative there. Okay, so then there exists a c on the open interval such that f prime of c is equal to, and this is basically slope of the tangent line through those endpoints. So here's your A, here's your B, and then so there's your line, right? So that's your secant line, and then there has to be a value c that gives you that same slope. And so what it's really doing is it's basically taking Rolle's theorem and defining a function and essentially putting it on its side like that. And you can see you get the same sort of idea. It's continuous, and you put it like that, and that's the slope of the secant line. So very important theorem used to prove a number of things. So I'm just going to do that. Okay, so next is Cauchy's formula, sometimes called the extended mean value theorem. And so this uses two functions and has a similar sort of result here. So let's go through that. So we're going to use Cauchy's formula to prove L'Hopital's rule, or to help prove L'Hopital's rule. So let's take a look at this, and we will go through the proof. So here we are. if F and G are continuous on the closed interval from A to B and differentiable on the open interval from A to B, and G prime of X does not equal 0 for any X in the open interval from A to B. Then there exists a C in the open interval from A to B such that, now this is where, if it was one function, you have the mean value theorem. So this is where you get this ratio. You get F prime of C over G prime of C is equal to the difference of the F's at the endpoints, F of B minus F of A, all over G of B minus G of A. So it's similar to the mean value theorem, right? I mean, it looks very similar, but now you have this ratio instead of this just one. So this, you're subtracting the endpoints of both functions and you get the same result. And so what we're after is, remember, we're taking a limit of f of x over g of x. So for L'Hopital's rule, let's go all the way back. There it is. We are taking limits, right, of f of x over g of x, and then it's similar to f prime of x over g prime of x. So that gives us, so now look at this. Here's, I mean, it's not exactly that, right? But you have your f prime and then f. So it's going to take some setup to do this when you actually prove it, but this is what we're going to use, a way to get from prime to not prime. So let's first, that's for L'Hopital's. So let's first look at the proof of this. Okay, so you say proof. So, and I want to go through all these, so I have them. I don't always go through this proof, just an FYI. So it's not like I need you to memorize it or do it. If anything, I'd have you just copy it, but I want you to try to grasp these concepts if you're shooting for a complete understanding of everything, or close at least. So let's assume, I'm not going to write everything out for the hypothesis. So let's assume the hypothesis is all true. So we are, f and g are continuous on the closed, differentiable on the open, and g prime does not equal to 0 for any x in the open interval. Okay, so it's all of that is your hypothesis. Okay, so we're going to need that, of course, for everything. So that's the hypothesis. So first, note that g of b minus g of a does not equal 0. If so, but let's just suppose it did. If so, g of b would equal g of a. And in that case, you'd be able to conclude using the mean value theorem, or actually Rolle's theorem. And by Rolle's theorem, there exists a w in the open interval from A to B such that g prime of w equals 0. And that would contradict our assumption. And would contradict our assumption. All right, so just to be clear here, so our assumption is all of this up here. Right here, we are assuming that G prime is not equal to 0 for any x in that open interval. So if this were the case, or if this were the case, you'd get this, and by Rolle's theorem, you'd get this, which contradicts our assumption. So this can't be true, or this is true. It's never equals 0. So now the next tough part here is we're going to define a function that behaves like we want. Right, so this is the part that after, maybe years of studying mathematics, and you have nothing better to do, you figure this out. All right, so let h equal this function. H of x is equal to f of b minus f of a times g of x minus g of b minus g of a times f of x. So we're going to define h of x to be that function for all x in the closed interval from a to b. All right, so now keep in mind now we are assuming g, f, and g are continuous. Okay, that's our assumption, and differentiable. So therefore, h is continuous on the interval, right? So h is continuous on AB, because it's just algebraic sum and difference of f and g. And similarly, it's differentiable. So, and differentiable on the open interval from AB. And that's because of differentiability, sum and difference of differentiable functions, differentiable, etc., that kind of stuff. Okay, so now we're basically stating the hypothesis of what we get for Rolle's theorem. Okay, so h is continuous and differentiable in that. And you have that h of a equals h of b. Okay, that's not necessarily obvious, so I want you to check that. So plug in a right here, plug in b. If I do go through this proof, this is an exercise I have you do. So I want you to check that. So check this. Okay, I'm not going to do that here. It's just some algebra stuff. And so if you have the endpoints equal and the hypothesis satisfied, you can say by Rolle's theorem, there exists a c in the open interval such that f prime of c is equal to 0. So there exists a c in the open interval from a to b such that h prime of c is equal to 0. And so let's do that prime. Right now we're going to take h prime and see what you get. So that is, henceforth, what you have is f of b minus f of a times g prime of c minus g of b minus g of a times f prime of c, because you're just taking those derivatives, each of those, which is h prime. So this is h prime. I probably should have just said that. So h prime is this. So I'm just rewriting it putting what h prime is. H prime of c is that derivative, which equals 0. And that basically gives us what we want. So now you can just take this, and then you add it, divide out appropriately, and you're done. Okay. And so, yeah, so that's it. So you basically just have, I'll rewrite this next step, f of b minus f of a, g prime of c is equal to g of b minus g of a, f prime of c. And so you just divide both sides by the appropriate terms, and you got it. Okay, so that is this. It has been proved. So this hinges around applying Rolle's theorem to a special function, to this special function that's defined, that behaves in the way we want. That's essentially how you do the same thing with the mean value theorem, the regular one. Okay. So we're going to use this part here and some other finagling to prove L'Hopital's rule, at least one of L'Hopital's rules. Okay, so that'll be next. I will restate L'Hopital's rule, and then we will go through the proof, and we'll just have a proof on L'Hopital's rule.